Welcome, and thank you for joining this webinar, From Connectivity to Sensing Revolution, How Wireless Can See the Invisible, prepared by Alpert Research Team. Today, we're exploring how wireless sensing isn't just another buzzword, it's the fusion of communication networks with environmental awareness, turning everyday Wi-Fi routers and 5G towers into silent sentinels that detect motion, monitor health, and optimize cities without adding hardware. So these applications are incredibly diverse and powerful, but making them work reliably requires a robust system architecture.
Absolutely. The whole pipeline needs to be carefully designed. It generally starts with raw data collection. That could be CSI streams, radar echoes, UWB pulses. Then comes a critical signal processing and feature extraction stage. And finally, the machine learning ML prediction or classification step.
Let's talk about that signal processing part first. Raw sensor data is noisy, right? Especially CSI in a real room. How do you clean it up?
Denoising is essential. There are several techniques. The Kalman filter is a classic and very powerful tool. It's essentially an optimal prediction algorithm that can estimate the true state, even with noisy and incomplete measurements.
How do you separate the signal you want, like a person breathing, from all the background clutter, the room itself, furniture, maybe a fan moving?
That's where techniques like background subtraction come in. The system learns the static signature of the room and subtracts it, leaving behind the dynamic signals caused by movement. We also use more advanced adaptive filters, sometimes combinations like ensemble empirical mode decomposition paired with CWT, continuous wavelet transform.
Okay, so the signal is cleaner, but it's still potentially very complex, right? All those CSI subcarriers. How do you make it manageable for an AI model? Feature extraction and dimensionality reduction.
Exactly. Feeding hundreds of raw subcarrier values directly into an ML model is usually inefficient and can even hurt performance due to the curse of dimensionality. So we extract meaningful features.
Like what?
The most basic are the amplitude and the clean phase values themselves. But we often derive more sophisticated features, like the power spectral density, PSD, which shows the signal's power distribution across different frequencies, great for capturing motion speeds, or various statistical features calculated over time, Windows mean, variance, skewness, etc.
But that could still be a lot of features. How do you boil it down?
That's where dimensionality reduction is critical. Techniques like principal component analysis, PCA, are very common. PCA finds the underlying patterns, the principal components, that capture the most variance in the data. Studies have shown PCA works well even as the number of input features, like subcarriers, increases. It's effective at reducing, say, 64 subcarrier features down to maybe 10 principal components that retain most of the important information, making the subsequent ML task much easier and more robust. Independent component analysis, ICA, is another related technique used to separate mixed signals.
Now we feed it to the AI and ML integration part.
The trend for HAR is definitely towards hybrid models. Architectures that combine the strengths of different types of neural networks are showing the best result, like combining convolutional neural networks, CNNs, with recurrent architectures, such as LSTMs, long short-term memory. CNNs are excellent at extracting spatial features from data. Think of them as learning filters that recognize patterns in the CSI image. LSTMs, on the other hand, excel at understanding sequences and temporal dependencies, how patterns evolve over time. The CNN-LSTM combination captures both the spatial characteristics and the temporal dynamics of human activities, leading to higher accuracy.
Now, one of the biggest real-world deployment headaches must be the domain shift problem.
Domain shift is a killer for practical WST. The wireless channel is unique to every single environment. The exact pattern of reflections, the multipath effects, they depend entirely on the room's geometry, the furniture, the materials.
So a model trained on room A's fingerprint is completely lost in room B.
Its entire database of learned reflection patterns is irrelevant. This is where domain generalization becomes absolutely critical. We need models that can generalize from the environments they were trained on to new, unseen environments.
The big strategic takeaway seems clear. We're really moving beyond just connectivity. We're turning signal interference, which used to be a nuisance, into valuable insight.
So what does this all mean? The message is clear. This wireless technology isn't just enhancing networks. It's enabling a sensing revolution that redefines interaction with the physical world. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.